Students, good morning. Today we are going to discuss a very important law, and this is the last topic of our second chapter. Second chapter is so short, isn't it? So it's law of conservation of linear momentum. Law of conservation of linear momentum. Fine, you know what is linear momentum, isn't it? It is the measurement of, or it is the product of mass and velocity. P is equal to mv. That was the equation for linear momentum. So what this law of conservation of linear momentum states is that the total linear momentum of two bodies after collisions remains the same as the same linear momentum before collision. Let me state it in one more sentence. That is, if two bodies collide each other, collide means കൂട്ടിമുട്ടുക. If two bodies collide each other, the total linear momentum of these two bodies will be the vector sum of the linear momentum of individual ones. That is, if here it is m1 v1 and if here it is m2 v2, the total linear momentum of the bodies will be m1 v1 plus m2 v2. That's total linear momentum. That is a constant always. That is what law of conservation of linear momentum states. In one more words, what we can tell is linear momentum before collision is equal to linear momentum after collision. So let a body with mass m1 and initial velocity u1 and another body with mass m2 and initial velocity u2, they collide each other. So before collision, what is their linear momentum? m1 u1 plus m2 u2, isn't it? mv is the equation for linear momentum. So here, as the velocity is u1, that is initial velocity, for that we take u1. If it is u1, we can write the linear momentum is m1 u1 plus m2 u2. That is the momentum before collision, which will be equal to momentum after collision. So after collision, there will be no change in the mass. Mass will be same, but initial velocity will be changed into final velocity, m2 v2. That's all this law tells. That is, momentum before collision is equal to momentum after collision. Or generally we can state total linear momentum of a system is always constant. That is what law of conservation of linear momentum states. You will understand about it more when we are discussing an example. So let us go through an example. Suppose there are two bodies A and B. Two bodies with different masses. Okay. And this A and B, they are moving in the same direction. Let the speed of A greater than B. That is, at the speed of, let me give the initial speed as UA. UA. For initial velocity, we represent it by using the letter U. As I give UA is greater than initial velocity of ball B. Then we can write UA is greater than UB. Then what happens if A is traveling with more speed than B? After some times, what happens? They are moving in the same direction, but as A got more speed, after some times they will collide each other, isn't it? After their collision, they will go in separate directions or sometimes in the same direction itself. Isn't so? As A got more speed, what happens after some times? Obviously, they will meet each other. As B is going very slowly and A is following it with very much speed, what will happen? They will collide each other after some moment. So, we are calculating the linear momentum and we are proving the law of conservation of momentum in this case. See, let us take mass of ball A equal to MA. So you have to write MA is equal to mass of ball A. Mass of ball A. Mass of A. Then UA is equal to initial velocity of A. Now next one, mb is equal to mass of B, ub is equal to initial velocity of B. Now after collision what happens, their velocities may change, so they travel with different velocities. Now the final velocity becomes Va, that is the final velocity of ball A, that is final velocity of A, and Vb is equal to final velocity of this A, this final velocity of B. So let me tell once more, let Ma be the mass of ball A, mb the mass of ball B, we are using to represent that mass, and ua is the initial velocity of ball A, ub is the initial velocity of ball B. So after sometimes as ua greater than ub, what happens, they collide each other and now they travel with a different speed. It's not the same as in the case of initial speed. So their final velocity for the ball A is given by Va, and final velocity of ball B is given to be Vb. Is it clear? Ma mass of A, mb mass of B. Initial velocity of A is ua, initial velocity of B is ub. Final velocity of A is Va, final velocity of ball B is Vb. Okay, don't confuse each other. Now as ua is greater than ub, after sometimes they collide each other. Now we know that according to Newton's third law, force acting on an object, if there is two objects A and B, if A is acting a force on B, then what is Newton's third law tells us? It got an opposite and equal reaction back on B, so that is minus FBA. So for every action there is an equal and opposite reaction. This is the action force. If A is acting a force on B, that means B is applying a force on A within the opposite direction. That is represented by using Newton's third law. So we have, according to Newton's third law, FAB equal to minus FBA. See, we have mass and velocity for ball A and ball B. How can we calculate force from mass and velocity? We know only one equation. What is that? F is equal to ma, mass into acceleration. But we don't know about the time, so we can't find acceleration, isn't it? So just go to the Newton's second law. What is Newton's second law statement? That is, rate of change of momentum is directly proportional to the force applied, isn't it? So we get an equation for force from Newton's second law, that is rate of change of momentum, that is change in momentum of A divided by time, that is rate of change of momentum of A. Instead of FAB we can write change in momentum of A divided by T is equal to, what is equal to, minus of change in momentum of B divided by time. What is that? Change in momentum of A divided by time, that is rate of change of momentum of A is equal to minus rate of change of momentum of B. So according to Newton's third law we got this equation. As T is coming in the either side, we can cancel this T. So what is left there? Change in momentum of A is equal to minus of change in momentum of B. Now let us find the change in momentum of A. Let me rub this and I will be finding it here. Okay, fine. So if there is a body A with mass m and its initial velocity and final velocity we know, what will be the change in momentum? If there is final momentum and initial momentum, final momentum minus initial momentum gives us the change in momentum of A. What is the final momentum? So we can write final momentum, that is, instead of change in momentum of A, we can write final momentum of A minus initial momentum of A is equal to, let me rub this one also, change in momentum is equal to minus of final momentum of B minus initial momentum of B. So just I convert this change in momentum of A into final momentum of A minus initial momentum of A. So what will be the final momentum of A? It is MA VA. Mass into velocity gives the final velocity, isn't it? MA VA minus initial momentum of A, MA UA, is equal to, what is final momentum of B? We have to put this minus symbol here. What is final momentum of B? That is MB VB minus initial momentum of B, MB UB, isn't it? So now let me rub this also. Once again, we come from the Newton's third law. According to Newton's third law, FAB equal to minus FBA. Force means change in momentum by time, or rate of change of momentum. So we cancel the time, we got final momentum of A minus initial momentum of A is equal to minus of final momentum of B minus initial momentum of B. So what is final momentum? MV, that is MA VA. Initial momentum is MU, that is MA UA. Final momentum of B, MV, that becomes MB VB. As it is in the case of B, initial momentum MU becomes MB UB. Fine. Now let me open this bracket. So when I open this bracket, this minus will be given to MB. So it becomes minus MB VB, minus into minus, it becomes plus MB UB. So here, just writing the same here, MAVA minus MAUA. I haven't made any change here. See, here I made a change. Minus is given into the bracket. So the first term got a minus and the negative term become positive as we multiply this minus with here, with the second term. Now let me take this negative term to here and this negative term to here. So when I take this negative term to the left side, it becomes positive. That is MAVA taking this negative term to here, plus MBVB, it becomes positive as it reaches here. Now I am taking this negative term to here, MAUA plus MBUB. See, MAVA plus MBVB equal to MAUA plus MBUB. What is similar in the two terms? Final velocity, final velocity. Here it is initial velocity, initial velocity. What is MAVA? Final momentum of A. What is MBVB? Final momentum of B. What is MAUA? Initial momentum of A. MBUB is initial momentum of B, isn't it? So that is, in total we can write momentum after collision equal to momentum momentum before collision. So that is the conclusion where we reached. So from here, from the what we can tell Newton's third law, that is from every action has a equal and opposite reaction. From there we reached into the proof of law of conservation of linear momentum, that is momentum after collision equal to momentum before collision. That is the total linear momentum remains constant. That is the thing we got from the law of conservation of momentum. See, once again we have to consider two bodies A and B, and they are moving in the same direction. You have to give an introduction like this. Suppose two bodies A and B, they are moving in the same direction. Let the body A is moving with more speed or more velocity than body B. So after some times they will collide each other. After collision, their velocities may change. Therefore, MA gives us the mass of ball A, MB gives mass of ball B, UA gives the initial velocity of A, UB gives the initial velocity of B, VA is the final velocity of A, VB is the final velocity of B. Now, according to Newton's third law, FBA equal to minus FBA, FAB equal to minus FBA, and therefore rate of change in momentum of A divided by T is equal to minus rate of change of momentum of B divided by T. Cancelling T, we got rate of change of momentum of A equal to minus of rate of change of momentum of B. Rate of change of change in momentum of A means final momentum of A minus initial momentum of A. Change in momentum of B means final momentum of B minus initial momentum of B. So when we minus them, we got MAVA minus MAUA equal to minus of MBVB minus MBUB. And finally, we reached at the term MAVA plus MBVB, that is all final velocities in one side and all initial velocities in other side. That is momentum after collision is equal to momentum before collision. Hence the proof for law of conservation of linear momentum. You will be asked to write the statement of law of conservation of linear momentum and the proof of law of conservation of linear momentum. Hope this section is clear. Thank you for watching. Have a nice day. You have to watch this 2 or 3 times until you are clear with the topic. I know it's a long video, but we have no other way. We have to conclude it in one video itself. So sorry for having a long video on this, but watch the video twice and clear your doubts. And you can also personally message me or either in our subject group. Thank you for watching.